All right, now that we've got the logs, since we've practiced our logarithms, let's go ahead and jump into the first part of first order kinetics. All right, so first order kinetics for any general reaction, A goes to B, and in this case we really just mean the reactants, and B we mean products, right? It doesn't have to be a one-to-one stoichiometry like this. The reaction can be more complex, but we're just using A in general to mean the reactant or one of the reactants, and B as the products. Okay, so for any reaction in which A goes to B, first order reaction are those for which the rate obeys this simple law. Rate equals some constant, which we call the rate constant, times the concentration of A. All right. We talked about these when we were talking about rate laws initially a little while back. And what this means is that the rate is directly proportional to the concentration. So if we plot the concentration on the x-axis and the rate on the y-axis, then this relationship would give us a straight line, and the slope of this line is k, the rate constant. We did some of those a while back, early in the chapter. So where do first order reactions come from? Let me see if I think I've got this. See if I can make this pop up. All right, yeah, all right. So a couple of examples. Decomposition reactions very often are first order. Not always, but a lot of times a decomposition reaction just involves breaking a simple bond, and so you can have things like this for N2O4 dissociating, coming apart into two parts as N2O. That's a simple first order reaction. Nuclear decay processes, for example, the decomposition of uranium, right? We haven't talked about nuclear reactions in this class yet, but uranium can spontaneously decompose to make thorium, and when it does, it gives off a little helium nucleus. Right? These nuclear decay reactions are also first order. Later in this section, we talk about first order reactions. We're going to talk about half-lives, and half-lives, of course, are something that you probably associate with nuclear decay. And finally, any reaction can be first order. It can be more complicated reactions than the examples I just gave, as long as the rate determining step is a unimolecular step. If the rate determining process is unimolecular, then you're going to get first order kinetics. Okay. All right, so let's take a look at some of the equations associated with reactions. Okay, so as we said before, the primary equation, the definition basically, of a first order reaction is that it's a reaction for which the rate is directly proportional to the concentration of the reacting species, the reactant A. Right? And from this equation, if you know differential equations, advanced calculus, you can use this equation to derive a general equation for the concentration of A as a function of time. We're not going to do that here, but you get an equation that looks like this. And this A sub T is concentration of the reactant A at some time t, 100 seconds from the beginning, 200 seconds from the beginning, 2 days from the beginning. Depends on what the speed of the reaction is, right? And this A0 is the concentration of species A at time equals 0, which of course just means the initial concentration. T in the equation up in the exponent. T, of course, is just time. I'm going to mention, well, we'll come back to it. We'll talk about units in a minute. And K is the rate constant. Okay. And you may remember previously when we talked about rate constants, the units for a first order rate constant are reciprocal seconds, okay? Or more generally, reciprocal time, okay? So the units for time are typically going to be in seconds, okay? But if the reaction is much slower, these could be minutes. So you'd have time in minutes. The rate constant will also be in minutes. For some environmental processes and some very slow reactions, time could be in days. And for nuclear decay processes, like we mentioned a little bit ago, the rate constants and the time intervals that people consider are years or hundreds of years even. Okay. Now the concentrations, typically concentrations are in molarity. Units for A at time t and A at, this is a 0, it doesn't look very good here. There we go. So the concentration for those, the units for those are usually molarity, but they can be different. And part of the key here is that this rate constant, since the rate constant is just reciprocal seconds, there's no concentration in K. So the rate constant can actually be in molarity or parts per million or percent composition. It can be in a bunch of different kinds of units, and it still works out because the rate constant doesn't have that doesn't have units of concentration in it. All right. So if you plot this equation, you want to know what concentration of the reacting species looks like as a function of time. I'll clear a little space here. This will look kind of familiar, I think. All right. So what this means is concentration of the reacting species, if you plot it as a function of time, has this familiar shape here, and the concentration then sort of asymptotically approaches 0. So this curve, as we've seen before, this is a very characteristic, it's a characteristic part of first order reactions. When you see that shape, you can be pretty sure that the reaction is probably first order. We're going to look in a little while, we'll look at second order reactions, which are similar. And we'll talk also about how to distinguish between first order and second order if you're not sure. All right, so we've got our equations here. Now let's look at an example. All right, so here's an example of a reaction. Formaldehyde reacting with water to make methane diol. And formaldehyde, probably heard of formaldehyde. Formaldehyde is just this simple carbon compound, right, with one double bonded oxygen, and when it reacts with water, it makes this compound that has 2 alcohol groups on it. And this is called, has a bunch of different names, but methane diol is one thing that it's called. It's also called methylene glycol. And I mentioned the names for this Doesn't actually have anything to do with first order kinetics. We will be looking at the kinetics in a minute, but I just wanted to mention something interesting about this reaction. Anytime you put formaldehyde in water, it's going to make this methylene glycol. And this methylene glycol is one of the active ingredients in a special hair treatment called a Brazilian blowout. I don't know if you've ever heard of that. I'd never heard of it. But you can see here's an example of a woman who's had a Brazilian blowout performed on her to straighten her hair. It looks nice. But there's an interesting problem with these in that formaldehyde is very toxic. And the company that was making the hair treatment for these Brazilian blowouts listed in the ingredients, they listed methylene glycol, but they didn't list formaldehyde. And it turns out that this reaction, we'll look at this when we get to equilibrium, which is the next chapter. Look at this. Formaldehyde reacts with water to make methylene glycol, but methylene glycol can also react with water to make formaldehyde. Right? So, in a sense, having a solution of methylene glycol is really essentially the same thing as formaldehyde. Besides, if you take formaldehyde, if you ingest it and it gets into your body, it's going to react with the water in your body and make methylene glycol anyway. So, the Brazilian blowout hair treatment contained this methylene glycol and was very toxic, or arguably toxic. I guess that's still under dispute. But because they listed as the ingredients methylene glycol and didn't list formaldehyde, they said that it was safe. And there were some lawsuits here. There was a suit filed by the state of California against the company that made the Brazilian blowout and forced them to relabel things. Anyway, kind of fascinating. But again, you guys really want to do kinetics, don't you? Okay. All right. So let's clean this up a little bit. All right. So this this formaldehyde, this is our reactant, so that'll be our A and B, and we just want to track the concentration of A as a function of time. And let's take a look at that on the next slide. All right. Okay, so here's some data collected for this reaction. We've got time from 0 to 1,000 seconds, and then we're tracking the concentration of, again, A here stands for the reactant, so this is really concentration of formaldehyde. Right. Concentration of formaldehyde as a function of time, and you can see that the concentration, if we track it here on this thing, it follows that same kind of path that we saw on the previous slide. Now, in a minute, we're going to do some calculations with these, and when we do them, it's difficult to try to call these things back up. That's one of the nice things about being in the classroom and having a chalkboard. We can leave the data and the graph up while we solve the problem. We can't do that here. So please take a minute and copy down this table, and probably also be nice to at least give a little bit of a sketch for this graph. You don't have to spend a lot of time on the graph, but take a minute to copy down this data table and sketch the graph. We'll use those when we're looking at the problems on the next couple of slides. All right, so the first thing we want to do, since one of the characteristics, important characteristic of first order reactions this is rate constant, one thing we might want to do, would be kind of nice, would be to solve for K. So the first question we're going to ask is, what is the value of the rate constant for this reaction? And we can do this, we can solve this by going back to that equation we had up a minute ago. Concentration of the reactant at time t is equal to the initial concentration times E to the minus KT. Okay. Now, you could start throwing numbers in there if you wanted. but I think it would get kind of messy. Usually, I think it's a lot cleaner to do a little bit of the algebra first. So since we're trying to solve for k over here on the right-hand side, let's try to isolate that. So we'll divide both sides by the initial concentration of A, or A0. So this will give us concentration of A at time t divided by concentration of A at time 0. This is equal to E to the minus kt. And then, as we're doing previously, in order to get k all by itself, take this little part on the right hand side, we can get k by itself if we take the natural log. But if we take the natural log of the right side, we also have to take the log of the left side. All right, so we take the log of that and the log of that. And then what this gives us is natural log of A at some time t divided by the initial concentration of A equals negative kt. All right. And now we're close to isolating k. We could divide both sides by t right now, but I'm going to go ahead and put some numbers in here and get rid of this messy log fraction on the left-hand side. So let's go ahead and do that. All right, so concentration of A at time t, that can be anything, right? We have a whole table here. We've got the concentration at 50 seconds, 100, 200, 400, 600, 800, 1,000, right? You could choose any of those. Let's go ahead, let's see, when I did this, I chose 200, okay? So let's just pick 200. Maybe you can guess what I'm going to tell you in a little while. Okay. So the natural log at 200, the concentration is 0.319 molar, and the initial concentration is 0.450 molar. Okay. The molarities cancel out, and that gives us a unitless fraction here. That's good, that's what we want. So this equals negative kt. Okay. And I'm running out of room. Make sure you got that in your notes. I'm going to erase this, and then we'll finish the rest of the problem. Okay, give me just a second to erase. All right, so I cleared a little bit of space. This is the same equation we had before. So the natural log of 0.319 divided by 0.45, if you put that in your calculator, you get natural log of 0.709 equals negative kt. And let's go ahead and solve the left-hand side just by using the calculator and getting the log of 0.709. Since this is a decimal number, this is a number less than 1, the natural log is going to be negative, right? And that makes sense because on the right-hand side, we've got a negative over here, and we're going to want the negative on the left to cancel out the negative on the right, because both the rate constant and the time both have to be positive. Okay, so we need those negatives to cancel. Use your calculator, take the log of 0.709 and get negative 0.344 equals negative kt. Then if we just divide both sides by -1 or multiply both sides by -1, doesn't matter, right? Our negatives will cancel. Get that? And then we can divide both sides by t, because we're trying to solve for k. So we get 0.344 over 200 seconds equals k. And put that in your calculator, and you get 0.00172. Okay? And for the units, note that we've got seconds in the denominator, so the units on this are reciprocal seconds. All right. We can rewrite that with scientific notation. All right, and there's our rate constant. Okay, now the math here is, it's not hard, but it might be a little bit unfamiliar with the logs. One of the things I tell you all the time when we calculate a constant, you can probably say it yourself if you know what I'm going to say. A constant is a constant. So when we did that calculation, we did this based on 200, right? But we should have got the same result if we used 100 or 400 or 600 or 1,000, right? For any of those. So you might take a minute now, since this is a nice thing about videos, you can pause me, right? You can also say bad words to me. You can say, oh, dang it, why'd you do that? You can do whatever you want. But what I would say, go ahead and pause and then try another one of these. Try the values at 50 seconds or 600 seconds. See if you get the same thing. Okay. Remember, you might get a little rounding error in that last digit, but you should get approximately 1.72 times 10 to the minus third reciprocal seconds. Okay. If you're so inclined, and I hope you are, give that a shot. And then we'll go on to the next question. All right, so the next question is, what's the concentration of formaldehyde going to be 500 seconds into the reaction? Okay. Now, the first thing we ought to do is just look at our data table and figure out what a reasonable answer is, right? 500 seconds is right here, right? So somewhere between 0.226 and 0.16. So probably concentration at 500 is going to be maybe somewhere around 0.19, right? Now let's give it a try. Let's put our numbers in there and see what we get. So we'll start with that equation that we've been using. Concentration of formaldehyde at some particular time is the initial concentration. So 0 minus e to the kt. Okay. So concentration of A at 500 seconds equals the initial concentration, which is 0.450 molar, times e to the negative 1.72 times 10 to the minus 3 reciprocal seconds times 500 seconds. So if we look over here on the right side where that exponent is, we've got the rate constant, reciprocal seconds times 500 seconds. So our seconds are going to cancel out, and that is going to be unitless, and that's good, because anytime when you're doing math, if you've got an exponent, that exponent generally should be unitless. Okay. If your exponent is not unitless, there's a decent chance you've made a mistake. Okay. So we multiply those together, the seconds cancel out. Oops. That's not what I meant to do. So our concentration at 500 seconds is 0.450 molar. Is e to the minus. Multiply those two things together, we get 0.860. And so this equals 0.450 molar. Remember to keep our units in there. And for this part over here, just use your calculator, right? Use your e to the x key. E to the negative negative 0.86 is going to be 0.423, and multiply 0.45 molar with 0.423. Get, well, that was a good guess I had. 0.19039 molar, which we've got all of our data in 3 sig figs, so 0.190 molar. And note, that's just about what we guessed before. That makes sense because 500 is All right, 500's right in here. All right. So, just as I did before, since we're not in the classroom, you've got all the time in the world, I would encourage you to pick a couple others and give them a try. You could, if you wanted, you could try to estimate the concentration at 75 seconds, right here, right? So it's somewhere between 0.413 and 0.379, so maybe, let's try green, we haven't done green before. Yeah, 75 seconds. Concentration should be somewhere around 0.40, maybe 0.39. I don't know, something like that. But definitely somewhere between 0.413 and 0.379. So you can pick some values in there, try to calculate them, see if you get things that make sense. If you want, you could also just pick one that's in here. You just pick 800. Let's say, what's the concentration at 800? Put 800 seconds in for T and see what you get. And if you get 0.114 molar, then you're doing everything right. So I would encourage you to try one or two of those until you feel good about it. All right. Third question I'm going to look at. How long will it take for the concentration to decrease to 0.050 molar? All right. So if we look down here at the bottom of this table, right, down here, it's decreasing between 800 and 1,000. It goes down by about 0.03, right? And if we're trying to go down to 0.05, that's another 0.03 that it needs to decrease. So if that decrease took 200 seconds, that decrease is probably going to take about 200 seconds. So, maybe somewhere around 1,200 seconds, right? Don't know for sure, but that's probably a decent estimate. Okay. Let's give it a shot. Let's see what we get. Start with the same equation that we've been using all the time. This time, our unknown is T. We're trying to solve for the time. So let's isolate that by dividing both sides by concentration of A0, concentration of A at time T, 0, E. Let me move that over a little bit. I'll show you why in a minute. It's E minus KT. And then in order to get the T out of that exponent on the right-hand side, remember we do what we've been doing. Take the natural log of both sides. And this is going to give us natural log so over on the right side, natural log of e to the minus kt, this is going to be minus kt. Okay. And in this particular case, we don't know what T is, but we know that the concentration at time T is going to be 0.050 molar, and our initial concentration, 0.450 molar. All right, and give me a minute, I'm going to clear some space for us. All right, so we had natural log of 0.05 molar divided by 0.45 molar. Put that in your calculator, and that is 0.1111, right? That's 1/9 basically, right? Negative KT. Now, again, because this number, the 0.1111, is a decimal number, a number less than 1, we'd expect the log to be negative. Put that in your calculator, and sure enough, it's negative 2.197, negative KT. And then we can just multiply both sides by negative 1, which cancels out the negatives. We get 0.2197, or excuse me, 2.197 equals KT. So let's divide both sides by K. It's T. And I'm going to clear space again. All right. So this is 2.197 divided by K. And remember that K is, what the heck is K? 1.7. 1.72 times 10 to the minus 3 reciprocal seconds. All right. That's T. So we can just divide these, and remember, when you have units, like the seconds here, units that are in the denominator of the denominator move up to the numerator, right? So we divide that through, and we get 1277.5 seconds, right? Which, if we round to 3 sigma figures, it's 1280 seconds. It's a little bit more than we'd estimated, but still in the same ballpark, so that gives us some confidence that we've done that one correctly. Okay. All right, and as before, you've got a bunch of data here. You can do this same calculation on your own. Try it a couple of times. You could say, for example, concentration of A is 0.200 molar. At what time was the concentration 0.2 molar, right? We don't know, but we know it's somewhere right in there, right? Somewhere between 400 and 600 seconds, so it should be, around 500 seconds. So you can do some problems like that to check and see how you're doing, see if you get answers that make sense, answers that seem like they're reasonable. You could also just take a number directly off of the table and say, at what time is the concentration of A equal to 0.379 molar? And put that in, do the same calculation, and when you do that, you ought to get 100 seconds, because that's that value right there. All right. So play around with those, practice a couple if you'd like, and then we'll move on. We've got one more question that we want to work in this data set. All right, so here's our last question on this particular data set. What is the instantaneous reaction rate at 750 seconds? First of all, just a reminder about instantaneous reaction rates. Remember on that first page, well, maybe the second or third page, when we introduced this data, we looked at the concentration of formaldehyde as a function of time, and it gave us a smooth curve that looked like that. This is typical for a reactant in a first order reaction. And as we did a few weeks ago, you can calculate the instantaneous reaction rate if you take that graph, and at 750 seconds, you just draw the tangent to the graph at 750 seconds, and then calculate the slope of the line using the change in the y-coordinate here and the change in the x-coordinate here. And the slope is the instantaneous rate. So if you want to go back to the first page and play around with that and calculate that, you can, but of course that's going to give you an estimated instantaneous rate, because everyone's going to draw their line just a little bit differently, right? Some people are going to be a little bit more up, some a little more down. So what we're going to do here is we're going to look at a way to actually calculate exactly what the instantaneous rate is at 750 seconds using the new equations that we've got that we didn't have a couple of weeks ago. All right, so let's take a look at this. The instantaneous rate at 750 seconds. All right. So this actually, if you just see a question that looks like this, it's a little bit deceptive, because this is really a three-part problem. Okay, and one is, since we know that this is a first-order reaction, right? What's the instantaneous reaction rate? We know that the rate, by definition, right, is the rate constant times the concentration of A at that particular time. All right, so in this case, it'd be the rate times equals the rate constant times the concentration at 750 seconds. Okay, but if you just get this problem, right, the first thing you got to do is figure out what's the rate constant, right? So if you hadn't already done that, that would be the first thing that you need to do, right? In this case, we've done that, and we know that it's 1.72 times 10 to the minus 3 reciprocal seconds, right? And then the next thing is what's the concentration of the reacting species at 750 seconds, right? If you don't have that information, then you need to calculate it. And it turns out we don't have that information, so we're going to have to do that. And then once you have both K and this concentration, then you can go back. You know what? Then you can go back and do that one. Let me renumber these. It's probably better to have said, well, this is step 1. What's the rate constant? This is step 2. And then once you've determined those things, then you can do this this one I have at the top. So that's really going to be our step 3. All right. So again, we've got the rate constant already. So the next thing we need to do is figure out what's the concentration of A at 750 seconds. You already know how to do that. I'm going to put the calculation up here, but I think I'm going to skip the narration on this and run through it a little bit quickly. Go ahead and do it yourself. Calculate the concentration of A at 750 seconds, and then we'll compare our results. Okay, so I went through this using the same equation that we've been using. Concentration of A at 750 seconds is the initial concentration times e to the minus kt. I just put in our values for initial concentration and K and T. Went through those and got a concentration of 0.12387 molar. And if this is our final answer, we probably want to round that to 0.124 molar, right? But since we're using this in another calculation, let's remind ourselves that it's only 3 sig figs, but let's not round it off quite yet. Let's use this number and put it in the rate equation. All right, give me a minute and we will do that. All right, so this is actually going to be kind of a record short summary. Really, although this was kind of a long video, we did a lot of calculations. Really only a couple things in here. One is that first order reactions, by definition, are those for which the rate law is rate equals K times the concentration of A. And you can use this equation and solve a differential equation from that, which we're not going to do, and I'm certainly not going to ask you to do. And that gives you concentration of A as a function of time. And remember, A is just some reactant in the reaction. Right. So this gives you the equation A at some times T is equal to the initial concentration times E to the minus KT. Right. There are 4 variables, right? Concentration at some time during the reaction, the initial concentration, the rate constant, and the time. And we talked about calculations we did examples of calculations on how to solve for all of those things. And you've got lots of opportunities to do practice problems because that one data set is very rich, so you can play with that all you want. Work through those and do some practice problems. You can also start doing things from the study guide, although there is a little more that I want to do with first order kinetics. So there's going to be a part 2 and a part 3, maybe a little bit shorter than part 1, but you can look for those coming up soon. All right, have fun with this, everybody.